This is the first in a series of videos where I'm going to talk to you about training robots. I'll take you all the way from deciding how to choose a robot to getting it installed, creating data, training, and then evaluating performance. You'll be able to create data like this. So you'll be able to use a leader robot to pick up objects like this little cube here, and then do a pick and place task. And of course, you can generalize to more complicated tasks. So we'll be gathering some data like this along the course of this series of videos, and I'll be explaining how these models work. Now, there are 4 initial videos I've planned. The first today about building versus buying your first robot. The next video then will be about the basics of how these models work. I'll cover 3 of the main models: the action chunking transformer, NVIDIA's GR00T N1, which is a pre-trained model that you just need to fine-tune, and then Pi0, which is also pre-trained and you can fine-tune. I will then show you how to train the ACT model, action chunking transformer, from scratch. And I'll show you how to fine-tune the GR00T N1 model. Now, those 3 videos are for later. Today, we're going to focus on the build versus buy decision. I'll start by giving you an overview of this robot here, which is called the SO1. I'll describe its motors and movements. I'll explain why I have 2 robots here, how that's useful for gathering data and can help us out with training. Then I'll talk about either building these by 3D printing the parts and assembling them with motors, or buying the ready-made robots. And last of all, I'll give you a quick intro to how the AI models work. It'll be somewhat cursory, but I want to repeat myself a few times over the course of this series so the concepts become clear. So I have 2 robots here. This one here is called the leader robot, and this one here is called the follower. The follower is the one that does the work, and you'll notice that the follower ultimately, well, you won't notice, but ultimately the follower should be operating on its own and doing this pick and place task of picking up the cube and putting it over here into the bowl. Now, to help the follower do that, it has access to 2 cameras. The first camera here, which we're calling a wrist camera, because the robot is able to twist its wrist like this. And there's also a camera you can see right here, which is a front view camera that's showing the whole picture, both the robot and its movements, but also the cube and the bowl itself. Now, you could just train with 1 camera. I've done it myself just using the wrist camera. But the more cameras you have, I won't say the more, infinite is maybe too much, but if you have 2 cameras, it's generally going to perform better than having 1 camera. Now, the way I have it set up here, I'm able to very easily look at what's happening when I move this one. And I am copying, well, it's copying me on the left-hand side. And this is deterministic. There is no AI involved at this point. Any movement that I make here, it will measure the rotation of the motor, and then it will try to bring this motor here to the same position as the one that I have for my leader. Now, because this movement here, you can't see it because it's very fast, but this movement is always going to lag a little bit, the leader's movement. And it's that difference in angle, that tiny bit of lag, that will drive a current that is going to cause this motor to move, to be in the same position as this motor. And that control is called a PID loop. It's a proportional, integrator, differential. These are the 3 terms that are used in the controller. You don't need to worry about that because it's all pre-programmed. But behind the scenes, what's happening is my motor here is changing position. It's leading the movement. And that gap between this motor's position and the recorded position here is allowing a current to be designed to give exactly the right movement to get it to copy. Now, why do I have 2 of these? I have them so I can create data. And this is something I'll do in later videos, but I'll be using this leader robot to pick up the cube very many times and create some different data sets. So I'll be able to pick like this. I'll be able to put it down like this. And we will have recorded the movements. Well, we'll have recorded the movements by camera here, and we will also record the movements of the leader, because the difference, again, between the leader's angles of the motors and the followers is ultimately giving us the signal for how we should control the currents, albeit automated behind the scenes. Now, just a few more notes on this here, which is an SO101 robot. That is a slightly updated version than the SO100. Both of them are described in great detail by Hugging Face, and I'll put links in the description. Now, let me describe the robot briefly, and then I'll describe what's different about SO101 versus SO100 and earlier robots like the MOS V1. This has got 6 different motors. I'll probably turn this one a little easier. it has a first one here, which controls the gripper. Notice how on the follower hand, it's in the form of a trigger, which is just easier. And on this hand here, it's actually a pincer. The second motor is the wrist, so you're able to rotate like this. The third motor is then kind of an elbow joint here. There's an udder joint right here. That's the fifth. Let me see if I'm counting right. 1, 2, 3. Sorry, this is the fourth. The fifth motor is here. And then the sixth motor is allowing me to rotate like this. So this is a 6-motor robot, and it's replicated to be the exact same on the follower rather, and on the leader. Now, the SO101 differs from the SO100 only in very small ways. The wiring here of the motors together is slightly better and more neat than it is in the SO100. The second difference is that in the SO100 design, the motors here are all the same. Every single motor is the same. And this causes a problem because when I want to manually move this leader robot here, if you have motors that are geared to provide the right strength, it makes it very hard to make movements like this. And so to overcome that, these motors are actually different in the SO101, and they allow me they're basically geared to be looser so I can still move them. In the SO100, you had to actually remove the gears from each of these motors, which was a bit of a pain because you'd have to take the screws off, take the gears out in order to loosen up. But this is all solved for in the SO101. So now I'll show you very briefly how we are going to train these robots. Quite simply, we're going to have, at any timestamp, we're going to have an image from this camera, an image from this camera, and we're going to have the motor positions, all 6 motor positions, fed into a transformer, to a neural net. And the neural net is going to be asked to predict the next sequence, not just one motor position, but the next sequence of maybe 10 motor positions. So for each of these 6 motors, the model is going to have to predict the 10 next timestamps, which could be, for example, at 10 milliseconds apart. They're generally going to be very close or very short time cadences between each of those timestamps. So ultimately, and you'll see this in all of the models we cover, we're going to typically predict a number of timestamps, not just one. It would be too slow to recursively predict very frequent ones. So we predict a full chunk. That's why it's called action chunking, you'll see. And they are all the future motor positions. And if we have the future motor positions, we then use the PID loop, the controller loop, in order to bring the motors to those future positions. So you can imagine that at every timestamp, we're going to predict 10 timestamps forward. We will then roll out, the robot will do that. It will take those 10 steps. And in that time, we'll have to predict the next 10 timestamps. And so we're going to keep doing that. We predict 10, move 10, predict 10, move 10, and there'll be some overlap in the computing movement. You can see that here on my slides. So a brief model overview. We have the wrist camera coming in as input. We have the overhead camera or the front camera, and we have the current motor positions. These go into a neural net, and they will give us predicted motor positions, typically 10 future positions for each of the 6 motors. So as an example, the current motor position, if we had a 1-motor robot, could be 30 degrees. The model will predict the motor positions for the next 10 timestamps, which might be in 20 milliseconds, 31, then 32, then 35, etc. The robot will execute those actions. That would take 200 milliseconds if it's 20 milliseconds per timestamp. And while the robot executes, the model will receive another image from the camera, another set of motor positions, and it will predict the next 200 milliseconds. So it's moving forward in chunks like this. And you'll see this when we train, but if you make the chunks of prediction too long, it becomes unstable towards the end of the prediction because it might veer off in a direction that's different from the reality of how the robot moves. But if you make them too short, on the other hand, then it can be quite hard for the computer to be done computing in time for the next set of predictions to be ready. So you have this trade-off where you want your horizon to be kind of long enough so you have time to compute, but you also don't want it to be too long because it becomes unstable. And there are some other considerations we'll see. Now, just in terms, there'll be a lot of terminology here. When we talk about the current motor positions, so the angles you see here, this is often called the proprioception. Another piece of terminology that I think is a bit misleading, we are typically predicting motor positions. Those are fed to the controller, and that is all handled itself. There's no AI involved. But sometimes we call those motor positions actions, which can be a bit confusing, but you'll often hear about actions or latent actions, and these really refer to motor positions that are being predicted. Here you can see that the predicted motor positions are going to be typically for the next time steps, 10 time steps. It will differ between models, but this will be the first model for ACT. We'll probably aim for 10 time steps for each of the 6 motors. So we're actually predicting 60 scalars here. We're predicting 10 times the number of motors. And each of these is a scalar that you can think of as going from some angle, maybe minus 180 to plus 180. It might be scaled differently, but you can just think of it like that. There is one other form of input that we will see, which is a text command. In the simplest ACT model, the text command is basically just some fixed token. But in the more advanced models like Root N1 or Pi, they are actually using vision language models, and those have got the ability to input text. So you could literally say, pick up the blue cube and put it into this container here. So there can be a text input as well. Everything, the text, the camera's input, the image, the overhead camera, and the current motor positions, they go through encoders. So they are converted into embeddings that will be the right size to go into the neural net. Often we will use off-the-shelf encoders. They're not shown here. Perhaps we would use a clip model for vision. Perhaps we would use a Gemma or polygemma model for doing text and images. So we will encode this information, pass it through the neural net, and then predict some motor positions. Now, how are robotic models different from LLMs? They are substantially different, I would say. Typically, they are not autoregressive. I've already said many times we would predict a chunk of motor positions in the future, not just one at a time. We won't autoregressively generate new words like we do in language models. One of the reasons for that is we need to be able to move very quickly to keep up with real time. And if you had to just do it one timestamp at a time, and each timestamp's only 10 milliseconds, it's going to be very hard to autoregressively decode fast enough. The second thing that's unlike language models is we don't really put in a history. In language models, we've got a whole sentence and we try and continue the sentence. But here we're just putting in the latest images. We're putting in the latest motor positions. So there's not this analogy of putting in the history. Now it actually could improve performance. You'll see in literature, if you put in even one historical set of motor positions, this can help a lot with smoothing. So that's a more advanced technique, but we won't see it within the models we're covering. Another difference with language models is we aren't outputting tokens. We are outputting motor positions, which are scalars. They vary from, say, minus 180 to plus 180, whereas in language models, things are quantized. We have specific tokens. So that's a difference. We'll also see, not in the ACT model, but in the Groot and the Pi0 model, that we will use diffusion models, much like how, say, any of those image models, Stable Diffusion, for example, Midjourney, those companies, they're using diffusion to create images, and we will be using diffusion to create a trajectory of motor positions. So we'll see that. Last of all, the models we're going to look at are generally small. They need to be small because they need to be fast to keep up with real time. If we used a big GPT-4 model, it would be very difficult to decode fast enough to keep up with real time and move the robot in the right speed. Now, I won't get into too much detail here, but I want to give you a quick idea of the robots, the models we're going to use. I talked about ACT, Action Trunking Transformer, Groot, and Pi0. They are all transformers. They all use the concept of attention, which means looking back and looking at the interrelationships between, say, images and text and images and motor positions. Groot and Pi0 are diffusion transformers, whereas ACT is not. It's a pure transformer. It's not a token-producing transformer, but it produces motor scalar values. ACT is not pre-trained. It's a very lightweight model. It's only about 200 megabytes. You will fully train it yourself in the third tutorial. Whereas Groot and Pi0, they are pre-trained. They have used large amount of data. Groot, interestingly, has used unlabeled videos, which means videos of robots where you don't know the motor positions. We'll talk about how that's even possible to do. And Pi0 uses a large amount of robotics data that is labeled, as I understand. Lastly, ACT. It's a simple model, it's fast, but it cannot multitask very well. Whereas the other models, they are capable of embodying many different tasks, and you can command them to do different tasks. particularly if you add fine-tuning for specific tasks. Note that none of these models we're going to cover are autoregressive. This isn't really seen in robotics. I expect maybe it'll be seen more in the future. Just like with audio, we've got more autoregressive models now. And none of these use tokens for motor positions, so there's no quantization of the motor positions here. If you did watch my series on time series, which is forecasting things like weather or stocks or anything in a time series, there's a strong analogy here between ACT and Patch TST, which is a lightweight time series forecasting model. It also predicts a chunk of future timestamps, kind of like ACT. And then there's kind of an analogy between Chronos and Groot. Chronos is actually autoregressive, but it's a pre-trained model, just like Groot. It's trained on a lot of data and can generalize very well for time series. Groot and Pi0 can generalize pretty well. At least we'll see if they do generalize in practice for any application, particularly if you fine-tune like Chronos. So I've done this in a bit of a different order, but what I want to talk about now is the question of building or buying. You have a few options. One option is to go all out and to build it yourself by buying the individual motors. So you can buy these little motors here on Alibaba. And of course, you'll need slightly different motors if you want the SO101 compared to the SO100. And you can then print using a 3D printer, which I'll talk about in a second, all of these parts. And this is a significant improvement on, say, the MOS V1, which was very nicely designed, but required you to put these brackets together. So there was no 3D printing, but the 3D printing makes it quite a lot easier. I will note that there can be some errors when you 3D print, and sometimes the screws, they don't hold very well. If you look here at my camera holder, which I have to screw in, it's actually missing. It's missing a screw here. And I did try put the screw in, but it got unthreaded, or it basically broke the threads. So I got a little bit of Gorilla Glue and I just glued it down there so that it's steady in position, because you probably don't want that moving, could cause some noise during the data collection. So you do have the option to print. If you print, the problem is you're probably not going to get the same price on these motors as somebody who's selling the full package. And also you need to have a 3D printer, which I'll talk about in a moment. So you'll have either the cost of buying a 3D printer, which is a cool thing to have, or the cost of somehow finding online somewhere to print them. So for that reason, I actually, even though I have a 3D printer and I've 3D printed some of the parts and I've assembled a MOS V1 before, I did buy this and I bought it for about, I think, €200, plus it cost me a little bit more because of customs and then shipping. But the beauty is I got this and I was able to get it running within probably a few hours. It's actually, the motors are already calibrated, so I just needed to do a more general kind of homing of the robots, which means just putting them in kind of a standard centralized position and then basically moving them through a full range of movement. I'll show you that on the third video. Either way, that allowed me to start quite a lot faster, and I think it probably was similar price or maybe not too much more expensive than printing stuff myself and then having to buy the motors and the parts in any case, because you will need to buy things like the camera. You'll need to buy, say, this holder here to hold this sturdily down. I bought these mats separately on Amazon just to have some kind of surface to protect the table. So you can find some links on the Hugging Face documentation, which I'll link as well, where I'll give a description of, well, Hugging Face is given a description of where you can directly buy these assembled, or you can order the individual motors like this. There's a parts list for the US, for the EU, and I think for outside of those two locations. Just with respect to 3D printing, I myself have got an Ender V3 SE, and it's a printer that's got a print plate of about 220 by 220, and it can print up to 250. That is actually not big enough to be able to print all of the parts at once, so you need to batch it into two. In hindsight, and I've had the printer a little while, I probably would have bought a Bamboo A1 instead, which has got a 256 by 256 millimeter by 256 height. And I think you can fit all or substantially all of the parts in one print. So you're going to save time in printing if you have the Bamboo A1 instead of the Ender V3 SE that I purchased. The Bamboo is a bit more expensive. It's definitely less than 300, whereas the Ender V3 SE, the Ender V3 SE, it's a complicated name. It's probably, you can get it for less than 200. That's what I got it for. So those are your options on build versus buy. If you do order it, probably you've got about a week before you receive it. So if you're interested in kind of following along, I'll be trying to release these videos on a weekly basis. For now, I've got a GitHub repo, as you might expect if you watch this channel often. It's called Advanced Robotics. It contains already some description of the build versus buy decision and some of the key links. And it's also got some scripts that I'm working on for training the ACT model and the GROOT model. And those scripts will become final and available on that paid repo. You can find more details at trelis.com/advanced-robotics if you're interested in having access to the scripts. If you're not in a position to purchase, I will try and describe as much as I can in these videos, so you can hopefully follow along with your own digging and a bit of help from ChatGPT too. That's it for this first video here on build versus buy. You can let me know any of your questions down below in the comments. Cheers.